Oh, shit.
Good afternoon, everybody. Looks like we have almost everybody here, just a couple more attendees that are set to join. So we'll get started. So today we are focusing on the Heating 101 overview. Craig Anderson is going to be our presenter. He's our lead TSA for Ontario Atlantic. I'll let him kick you off. Just a couple ground rules. If you need to ask a question, just feel free to put your hand up. I'll do a little bit of a demo here. So there's like a hand up symbol and you can put it down, or you can use the chat. That's another viable option. While Craig is speaking, if you could just put your computer on mute so there's no background distractions. And I'll let Craig kick us off here.
Good afternoon, everybody. Thanks for coming out. So like Megan says, I help head up the department for technical service advisors, TSAs we call them. So for Ontario, and I help out Atlantic Canada as well. So in Ontario, we have 2 full-time as of now. Myself and Guy, that's up north. We're in the process of hiring another full-time TSA in the Toronto GTA area, which should happen within the next couple of weeks. We're just finalizing who we're picking and how we're going forward with that. And then our game plan is to hire a 4th mid-year, so we'll have full time to help out anybody that's calling us, so we can answer you more quickly. Once we have the 4 full time, we'll still have a bunch of TSAs that are in the areas that are covering branches like Foria's, but we'll have 4 main ones hopefully by mid-year, but 3 for sure within the next couple of weeks. And I believe everybody has those phone numbers. If not, you can reach out to Megan and we can get that list out to your company. So today we're going to do, we're calling it Heating 101. It's going to have a little bit to do with your air conditioning as well. We're going to be talking about motors and airflow, and we're going to touch on the ion stat. We'll be about an hour, and then we'll get you back to work. So I always start off the presentations with this, GoKeepRight.com. This is your go-to site. No password needed to get it. This is going to give you spec sheets, installation manuals, technical manuals, product literature, anything you need to know on the Keep Right product with a certain time frame. Like I said, no password, GoKeepRight.com will bring you into this website here. So this is a new look. If you've been on the Go Keep Right before, you'll notice that the pages looks a little bit different, but same way to get yourself through it. So on the right hand side, you're going to have a little search box here. This is your go-to box. First 4 digits, 5 digits of a model number. Don't do any more than 4 or 5 digits. It'll just give you a whole bunch of different stuff that you don't need, or it just will not find anything. So once you put the 4 or 5 digits in that search box, hit search, it's going to bring you up installation instructions, homeowner manuals, warranty documents, technical service book. So if you're talking to a TSA on the phone, or even somebody from ICP, if we're doing a 3-way call, these are the sites that we go to get the information: troubleshooting charts, installation manuals on vent lengths, anything that you need. This is the great site. So program it into your phone, your laptop, anywhere. So it's GoKeepRight.com. So just do a quick product overview, and then we'll get right into our sessions. So model numbers of the furnace changed a little bit. This is our fully modulating furnace, 40% to 100%, modulates in 1% increments. It only modulates if you put it with a modulating thermostat. If you're putting a modulating furnace with a single stage stat or a 2-stage stat, it becomes a staging furnace. It does not become a modulating furnace anymore. So just be noteful if you're out there selling or you're working on one, if it doesn't have the modulating stat, it's not going to modulate properly. So it's a fully communicating unit. To make it communicating, we need to put that ion stat on it. The second one down is a G9E6 CTN. So this is their 2-stage communicating furnace with the ion stat. 4-way multi-positional, like any Keep Right furnaces that are out there. They all have the same cabinet widths, height, nothing changes. So this is the 2-stage 9E6 communicating. If we don't want a communicating furnace, then we have the G9E6 VTN. So this is a 2-stage non-communicating furnace. We can put a single stage stat on it or a 2-stage stat. if we're putting a single stage stat on it, it's going to take 16 minutes before it gets into second stage fire, high fire. So if you're doing your testing, setting your gas pressures to get it to second stage, to set your high side, you might want to jump it because it is 16 minutes. Just for setup purposes, you probably want to jump it out. And 16 minutes is a long time when you're standing there looking at a furnace. Same thing, 4-way multi-positional. Next one down, this is our single stage down and dirty furnace, 95%. This has the ECM motor in it as well, but it's an X13, so this is a speeded motor. If you get into houses where ductwork's a little finicky, stuff like that, you want to be able to pick your fan speeds. This is the furnace to do it. It's also mobile home approved, so any mobile homes with the proper kit, we can put it in a mobile home as long as you got enough room in that little closet. So motors and modulating controls. So this is our biggest thing, whether it's air conditioning or heating season. ECM motors is our biggest part. A lot of calls on how do I troubleshoot this motor? What do I need for it? So we'll go through that today. So here's our motors. These are the new motors in our new units. Fixed speed, so that's our X13. We have a variable speed constant torque, which is in our 2-stage non-communicating unit. And then we have our variable speed constant airflow, which is in our 97 and a 96% communicating furnace, which we'll go through. So 3 motors that we're looking at in our new series that we need to know how to troubleshoot when we're out there. So an idea what your ECM motor is looking like, usually have the end bell on it, what we call, that's the motor control. Then we have the motor, 3-phase motor. So we're changing voltage from 3-phase to single phase, or sorry, other way around, single phase to 3-phase going into our motor. Start windings and a magnet inside. So this is what we used to look at in our old furnaces. We used to have the whole PSC motor, 110 volt. That is not out there. We cannot get it in a furnace anymore, but we still have a lot of furnaces out there with them. Then we just had the basic X13 motor, which was in our 2-stage and our single-stage furnaces. And then we had the variable speed constant airflow that was in our communicating furnace. So that's the 3 motors that we had before, and I just showed you the 3 that we had recently now. So variable speed constant airflow. So this one here, like I said, it's a communicating motor. It's in our 97 and 96%. So this motor communicates with the thermostat and it communicates with the board. What we mean by constant airflow, as we'll notice down here at the bottom where the constant airflow is, you'll see that the static pressure is changing, but the airflow is not changing, or CFMs. This motor will do everything in its power to give you a constant airflow, a constant CFM, regardless of the static pressure. So if you have to look at, be in mind, if you have this furnace in a unit and we have real bad ductwork, this motor is going to work hard because it's going to try anything in its power to keep a constant airflow. So things to look at when you're out there selling now, because these motors work a lot different than a standard speeded motor. We need to look at static pressure. We need to look at duct sizing, filters that we're putting in it. So be very mindful when you're out there doing service, and we'll go over some static pressure readings later on. So this one's fully communicating, 97 and 96 communicating furnaces. So this one here is a variable speed constant torque. So this is in our 2-stage variable speed furnace. As you'll notice on the static pressure, because we're not communicating, we're doing our dip switches to change our speeds in our motor. So our board is actually doing whatever we tell it to do. We can go from -7%, +7%, into 15% of tweaking our motor speeds to allow for our temperature rise and our static pressures. But this one will only keep us a constant torque because it's not communicating. So you'll notice that our CFMs will decrease depending on our static pressure and our ductwork. Fixed speed, constant torque. This is our X13 motor that we're all pretty familiar with. This is a speeded motor, 24 volt terminals going to the board from the motor. Same as standard PSC. So here's our PSC, similar to our X13, but it's a PSC motor. Direct power to the motor, 115 volts. Pick your speed, whether you want it on heating and cooling, and away you go. Static pressure is going to determine what our CFMs are going to be on this motor. So just a summary of our motors, what we have out there now. We have the fully communicating motor in our 97 and 96% communicating furnace. We have the constant torque, which is the variable speed, which is in our 96 two-stage. Our fixed speed ECM X13 motor, which is in our N95 furnace. And then our PSC motors, which is in our older furnaces, our 92s and 95% way back. So PSC motors, pretty standard on our taps to test for servicing. We have our heating, cooling tap. Some will have taps for constant airflow. 110 coming out of the board to the motor. For not getting 110 out of that board to the motor, then we got a board problem. If we have 110 coming out of that going to the motor, then we have a motor problem, or we have a wiring harness problem. Always check the board and always check the taps on the motor. See if we have the same power at the start and at the finish. Always check your power to neutral and always check your power to ground to see if the readings are the same. If we don't have the same reading from power to ground and power to neutral, then we need to look outside the box. Do we have a grounding problem or do we have a neutral problem? Things to look at. So ECM motors, when we're working on them or if we're going to take them apart, we want to turn them off and let them power down. They have big capacitors inside that can give us a little jolt when we're working on them. We want to make sure that the motor is in the housing and it's under a load or a static pressure. ECM motors look for static pressure, they look for loads. So if they don't have any of that, if it's just sitting on the bench spinning, it's got no friction, it's got no static pressure, it could do some erratic behavior. It could be it could ramp up, could ramp down because it's searching for something. So just be mindful when you're checking it, make sure it's in the blower housing, it's secured in there, and we have it under a little bit of a load. So multi-tap, which is used in our N95 units and some of the earlier N92 furnaces. So X13, like we were talking about before. So this is a speeded ECM motor. So all ECM motors have a neutral and they have a black, which is our hot wire. There's always going to be 115 volts going to this motor at all times, whether the motor is running or the motor is off. As soon as this furnace is powered, all ECM motors should have power going to the motor. First thing to check, black and white, let's see if we got 110 volts. So on this ECM motor now, we're looking at our speeds, our cooling, our heating, our circulation. These speeds are all done with 24 volts, similar to a PSC. PSC, we're doing 110 volts. Our speeds on this motor are 24 volts. So we're going from a common to one of the speeds. If we're looking for heating, then that heating speed should have 24 volts coming out of that board going to that motor. If it does, and we have our 110 volts, chances are our motor is done. But always check at both ends, board and motor. We could just have a pin out. Good things to check. Speeded motor, 24 volts on our ECM X13 motors. A little closer view of where you'd be looking at your taps. So you're going to have your common, your heating, your cooling, and your fan speed. Some of the older versions, if it was a 2-stage with an X13 motor, you could have heat 1, heat 2, and then you have your cooling speed. So just be mindful of where you're connecting and what you're asking for to run. Whatever you're asking for to run, 24 volts will be coming out of that to your common off your terminal strip. Or you can do common right off your board as well. So here's what your 115 volt taps will look like. They'll all be pretty much the same on all boards. You're going to have your neutral spot where all your neutrals from your blower motor, your door switch, incoming power are always usually ganged up on your board. And then your power going to your fan motor is usually tagged BL1. So that's going to be 110 volts coming out of your boards to your motors at all times. So here's our fully communicating motor. This is our 97 and 96 communicating motor for our top 2 dogs. So each of the Keep Right furnaces have a couple similar things on the boards. We have a memory chip that's up here, which is called a model plug. Because the boards are being used in different furnaces, this model plug is actually telling this board that it's a 40,000 or a 60,000 furnace. So if you ever come down to changing your board, it's going to say right on the box and a big orange sticker, don't forget to take the model plug out of the old board and put it in the new board. If you forget it, the furnace will not run in heating. You'll get an error code, and then you'll be starting a search for what's going on. So be mindful of when you're changing the board that you're changing that little model plug up at the top. All the Keep Right furnaces as well, we have a setup switch, which will test a bunch of the components in the furnace. So SW1-6 will put our furnace into a test mode. We want to disconnect we want to take the thermostat out of the equation. I always say to take all the wires off the board. Let's eliminate everything. Let's start from scratch. Let's just get that furnace to run on our jumpers, and let's go from there. Thermostats, HRVs hooked up. Anything can do funky stuff to the boards if the stuff that's added onto the furnace is acting up. So let's get down to the start and eliminate everything right off the get-go and then work from there. So when we power up the unit and we set our SW1-6, what's going to happen is our inducer is going to energize at medium speed. It's going to stay energized. Our HSI is going to come on for about 15 seconds. Then it's going to turn off. Our blower is going to energize for 15 seconds at about 50%. Blower and inducer are going to stay energized at the same time. So we're testing the blower, we're testing the inducer, we're testing the hot surface igniter. The gas valve is not going to energize at no time. We're not testing the gas valve. We're checking our safeties and making sure what's going on in our furnace with this test sequence. So once the sequence is done, our furnaces with our error light, a steady heartbeat is normal operation. So if it goes through the whole test sequence and we have a steady heartbeat, that's telling us everything at this point that I've tested is working properly. So we can go on to the next step. You could get error codes of 2+5, 3+5 gas valve fault, blower motor fault, inducer fault. So kind of things that this test sequence is looking for at the start. And if it doesn't find anything, we're going to stick at a normal heartbeat. So once you're done the test and you figure out what the problem is, or you've went back to a heartbeat, you're going to have to flick that dip switch 6 back to the normal position, or it's going to go into an error code when you actually start hooking everything back up again. So always remember to put it back to the proper position. So when we get into modulating motors, inducers, stuff like that, there are specialty tools out there that help us. If we don't know how to test them, and if we don't know how have the tool, you're going to the branch and you're buying a motor and you're buying a control board and you're getting there and you're going to guess. So this tool assists in checking the motor circuit, sends a good motor signal to the CPU, the furnace board. It includes a 16-pin and a 4-pin conversion harness, depending on what motor that we're looking at. So this little piece is going to help you. You plug it in, it's going to send a good signal to the board. If the board is getting a good signal, then it's going to tell you if we have a faulty board. We've eliminated the fan motor because we're telling the board we have a good motor. Something else is still going on. So it's taking that guesswork and that testing out of the equation for you just by plugging it in. So connect motor harness to the simulator, verify that we have the line voltage, 115 volts all times. Perform your self-component test, SW1-6. And then let's see what the status code says on our board. This little device is telling us we have a good motor, so what else is happening? This little device also works on the inducer. So when we're talking about a modulating furnace, this furnace has a modulating inducer. It is an ECM inducer, just like the fan motor. Little different in testing. If you don't have the testing procedures written down, then it's a hard guess to which brown, yellow, blue wire I need to test. This takes all the guessing out of the equation. It sends a good signal to your board, and we can move on just by plugging it in. So after it does through our test signals, like I said, it's going to give you different faults, a 4+1 motor fault, communication trouble, things to look at. Your motor, did you put the chip back in when you changed the board? Are all the plugins in there securely? Things to look at. So our ECM motors that are out there, it's a 5-pin connector for the line voltage and a 4-pin connector for communication. So when we're looking at power supply in on these furnaces, as we were talking about before, all of them have a black, a white, and a green. So that's telling us if we have 110 volts, 124 or 120 volts to the motor. This is constant all the time. On a 120 volt motor, you're going to notice that there's going to be a little jumper in there. That's indicating that we have a 120 volt motor. These motors are used on rooftops, so without that jumper in, this motor can be used as a 240 volt motor. So just be mindful that jumper is in there when you're looking at your plugs, or if it's in there properly. So verifying control signal, like we were talking about before, always test your board, always test your motor. We could have a problem with the wiring harness or just the way it's plugged into your motors as well. Couple options of testing these motors is one, ECM motor tester. This is another tester for this style of motor. We can do it with our multimeter. You can do it with a little light if you're up for that challenge to test it. Chances are we have one of these two tools in our toolbox to do our testing. So this is the Testmate Pro for the ECM motor tester, made by Gentech. So the old style Testmate Pros never had the little 16 to 4 pin adapter. At that time, they didn't have motors that had different plugins. The new testers will come with all the adapters built in, the 16 and 4 pin right on the tester. Very easy to operate. Everything is hooked up to this tester. There's nothing to add on to it. As soon as you take it out of the box, it's ready to plug into your motor and plug into your gas furnace. So what we're doing is we're powering this Testmate Pro. We're bringing 24 volts to it. So we need to take 24 volts from the furnace, whether we're bringing it from RNC on our board or we're taking it right off the transformer. So once we bring power to this Testmate Pro and plug it into our motor, whether it's our 4-pin connector or our 16-pin harness going into our motor, we're plugging this directly into the motor. We're eliminating the board at this point. All we're doing is testing the motor. Make sure we have our 110 volts, 120 volts going to the motor. And then let's put this Testmate Pro on it. Get our 24 volts. Once you get your 24 volts, power up the furnace. That Testmate Pro is going to have an on and an off switch. It's going to light up green, and that's going to tell you we're ready to go. Flick the switch to on. If that motor turns on, that's telling us that the control is working, the motor is working. And we're going to go towards why our board is not feeding power to that motor. Pretty easy. We're not doing any multimeter stuff. We're just plugging it in, flicking a button, and away we go. Very handy to have those two pieces of equipment for testing purposes. This is all you're going to be dealing with for the next 10 or 15 years till something else comes up. These motors are going to be out there. This is going to save a lot of time for you guys on the job site. Plug it in, press a button, away you go. So if we're going to use a voltmeter, you're going to make sure that you have a voltmeter that's going to check DC voltage that is fluctuating. You're going to need long, skinny probes because we want to get in the back of the plugs. If you don't have long, skinny probes, couple things to do. If you have a paper clip, you can get a paper clip shoved in there and you can test off the paper clip. Stat wire works as well. Strip both ends, get your stat wire, jam it in there, and then you can test off that stat wire. So make sure you take it out after you're done with it. If you got long, skinny probes, then you're done. Just pull the little end off so your probe is long enough so you can get it into the back of the harness. We're always going in the back of the harnesses because we don't want to push the wire out of the harnesses. If we're checking it the other way, chances are we could push that wire out of the harness, and then when we plug the harnesses back into our boards or our motor, we could push it out even farther. So you could be there on your service call and figure out, hey, it's the fan motor, 100%, you did your job correctly. You go there, you change the motor, you pulled the wire, it came out of that plastic plug, you pushed it in, and it pushed it out a little more. The motor doesn't start again. So where are you? So always go in the back of the plug. When you're pushing the plugs back into the boards or the motors, after the plug is secured, take the wires and push the wires in as well. We want to make sure we have no loose connection. It just could cause a whole different problem on the job site. So if we're using our voltmeter terminal destinations from the bottom up, we're looking at a blue, a yellow, a green, and our red wire. So one's going to be our feed in, one's going to be our feed out, one's going to be our ground, one's going to be our neutral, and we'll go through this. So 12 volt DC supply, we're going to have going to our motor. We know we have our 110 going on our black and white. That's present at all time. We're looking for a DC voltage now on our green and our red. So we want to check both terminals. We want to check our red to ground. We want to check our red to common. We want to make sure we're getting the same voltage. We should have 12 volts DC constantly at all times. These voltage should not be fluctuating. We also want to check our grain. We do know it's a ground, but we want to make sure that we're not getting voltage on that. If we're getting voltage on that, then maybe we have something back feeding through that motor or somewhere else. So always check your grounds as well when you're checking your wires. And then now we want to check between our red and our green to see if we have our 12 volts present there as well. And like I said, it should not be fluctuating. So on our board now, we want to check our green, we want to check our yellow. This is our input signal from the board. Again, we want to check from common to our yellow. We want to check common to green. We want to check ground to green. We want to check ground to yellow. Make sure our voltages are steady and staying the same on both. And then we want to check them across. Yellow to green, 5 volts DC. You might get a little bit of fluctuation, but it'll be a little bit under, but it should be quite steady. It shouldn't be jumping around. So here's our output signal. So we checked our input signal going from our board to our motor. We know that signal is good. Now the motor needs to talk back to the board. So this is done on our green and our blue wire. Same process, common to blue, common to green, ground to blue, ground to green. And now we're going across the blue and the green. This should be a 0 to 1 volts DC. It'll fluctuate back and forth, but it'll pretty much stay steady. But you'll be getting, because it's just on the outskirts of a 0 volts DC. That's why you'll see that little jumping there. Same thing here. Once we're done testing it at the board, we want to test it at the motor to make sure that plug is in correctly, or the wires are, maybe there's something going on between the wires. Very uncommon that we see a wiring harness fail. If anything in the wiring harness is usually where the connections are. They're not pushed in enough, or it's just not sitting in there properly, and we need to replace it so it fits a little bit tighter. Very uncommon for the wire between the two plugs to be affected, unless there's something outside the box that has actually happened to it. So this is just like I stated, our readings that we're going to read to on the motor. Red to green, 12 volts DC, yellow to green, 5 volts DC. Blue and green, we should have a little bit of a fluctuation between 0 and 1. That's if you don't have the tester to plug into the motor. We can do with our voltmeter. So our variable speed constant torque, this is in our G96 VTM. There's no tester for this motor. This is all done by our multimeter. So we have to make sure that our multimeter can read DC voltage. Most do nowadays. So this motor here, standard in our 80s, 100s, our 60s, our 40s, we're going to be looking for 4 wires. We're going to be looking for our white and our black, which is standard 115 volts going to the motor at all times, no matter what. This one here will have a yellow and brown wire. Depending on the models, they have different plugins, but they're the same concept. Power going to the motor, power coming back from the motor to the board. Very easy to check. So we're going to insert our meter probe into the back, again, into the back of the probes on our brown. So brown is feeding our board. This is telling us our board is giving the motor the power it needs. So common from our terminal strip on our brown wire, we should have 15 volts DC constantly, similar to our 115 volts going to the motor. Should be constant. It should not be fluctuating up and down. Constant 15 volts. Some meters might be a little bit lower, some might be a little bit higher. My tester, if I usually test them, I usually getting just over 16 volts DC. So depending on the meter, you might be a little bit lower, you might be a little bit higher, but it should be a constant voltage. So like I was saying, lower or higher, it shouldn't be unstable. It shouldn't be ramping up and down. You should have a constant voltage on that brown wire no matter what. So now that we know coming out of the board and going to the motor, we have that DC voltage. We have our 115 volts on our power in. So we know the board is good. The board is doing the job. So now we want to see what the motor is doing. So similar testing that we've done on the brown, we want to do on our yellow. So the yellow, with no operation of the motor, we should have a voltage of 10 to 12 volts DC constantly all the time. So now before we have done anything, now we know we need 115 volts on our motor. We need an average of 15 volts DC on our brown wire, and our yellow, we should have between 10 and 12 volts DC. Nothing is turned on at this point. So we know our board is giving us our power. We're getting power back from the motor. So if we're not getting voltage back from that motor, if we're getting 0 with nothing running, or we're getting under 10, then we need to start looking at wiring harnesses or motor control issue. We know what we have our 15 volts DC going to the motor. That is constant. Everything is hunky-dory. Now we've tested our yellow. If we don't have voltage, or if we're under that 10 to 12, then we're looking at an issue before we even start. Same as if we don't have the 15 volts on the brown going to the motor. If we don't have that, or it's significantly under 10, then we're looking at, we have something going on with the power going into the motor. So once we verified all the power, we're good. We've got our constant voltage on our yellow, our brown, our power coming in. We're going back to our SW1-6 switch. We're turning it on. We want to see what this motor is going to do on our yellow wire. We know the brown's the feed in. We want to see what the yellow is going to do when that motor is supposed to start. So as I said, SW1-6, we're flicking on. We're going to put our probe in the back of our yellow connector, and we're going to go to common on the board. We're going to hit that switch, and then we're going to get ready to go. So before the motor starts, we should have 10 to 12 volts DC. So once it's going through the self-component test, our inducer comes on, our hot surface igniter comes on. Once we're ready for that blower to come on, our voltage on our yellow wire should drop. So instead of reading our 10 to 12, we should get a reading of between 6 and 8 volts DC coming from that motor. If we're getting significantly lower, that we're looking, because we know this is the feed from the motor. If our power on our yellow is wrong, then we know our motor is something going on, not our board, because our motor is talking to our board at this point. If we're on the brown and our powers are funky, then we know we're dealing with a board issue, because our board is talking to our motor. So once you get that set up, brown's talking, yellow is coming back, gives you an idea of what you should be looking at and how to test. So this is what we were looking at. Our brown wire, constant, 15 volts DC, in that range. Like we said, your meter will be a little bit different. Yellow wire from that motor, 10 to 12 volts DC, constant, steady. Only time it changes is when that motor turns on. Once that motor turns off, then that voltage should change back to 10 to 12 volts DC. At any point, if you're getting 0 on your brown or your yellow, browns are talking, yellow is coming back. So anything below 10 volts DC, reading, then we're looking at the problem of where it's generated, whether it's the board or the motor. Another way to check our older motors, whether it's our furnace or other manufacturers, the motor can be separated. 90% of the time, it was the end bell on the motor. As soon as you took it apart, you looked at it, the capacitors inside that little head were blown up. The acid is coming out of it. It was pretty easy to determine what the problem was at that time, was in that little head. But you can separate them and test this bottom part of the motor. So we're going to check the windings on the motor. So we're just going to do a winding test to each part of that motor. We're just going to go ground to each side. We should have 100K ohms on each one. Replace the motor if you're under 100K ohms. Pretty simple. We can also do a resistance check on the motor itself from A to B, B to C, C to A. We're just switching up the connections. Windings should be equal. Resistant values less than 20 ohms is what we want. So each winding's like checking a compressor if you're in air conditioning when you're checking that. Each reading on this one here, because we're dealing with a different motor, it's like your mini split DC compressors. When we're testing them, our resistance values should be equal on testing that motor. Another big thing that's we need to check if you're not doing it, do startup sheets, cover your butts. You want to make sure when you leave that building, you have documented everything that you have done. Somebody comes in behind you, there's no documentation. It's your word against theirs. Just cover your butt out there. So if we're doing a temperature rise on the furnace in heating mode, we're checking the supply and return temperature at the same time. It's a lot easier. 2 pocket thermometers, one in the supply, one in the return. Start your furnace, let it run for 10-15 minutes, get it running, make sure your temperature rises in the parameters of what is set on the furnace. High stage are usually between 40 and 70. Mid-range is great. We always want to stay away from the high end or the low end. If you're too low, then the people are getting cool air out of their register instead of lukewarm or hot. But always do your temperature rise, set your fan speed to what is needed. This is going to tell you if you have a bad filter. It's going to tell you if you have bad ductwork or a dirty coil. Filters out there in the market, there's 5-inch ones, 4-inch ones. They are fantastic. They're pleated. It's giving us a lot of airflow. We're running into problems with 3M filters that are out there. They're like cardboard. I've seen one change our temperature rise 30 degrees. They're crazy. That was new out of the package. So we really need to be mindful of our temperature rises. We used to get a lot of calls on code 3, which is pressure switches. We're getting more calls on code 4, code 7, which is high limit errors. And they go away when we take the filter out. So we have to be very mindful of what we have in there and what this furnace is doing. So temperature rise is one of those big things that we need to check. Static pressure is another big thing. Our fan motors are looking for a static pressure. They're running to look for static. So we have to be mindful. Our static pressure, good static pressure is about 0.5 to 0.8. Anything out of that, if you're too low, then your motor starts hunting. It starts looking for static pressure. If we're too high, then our motor is working too hard. So then we're going to have motor failures. on furnaces. If you're going back, I've changed the motor twice in 3 years. We need to start looking outside the box. We need to make sure that our coil is clean, our filter isn't dirty, or we have the wrong filter in there. So static pressure is a big thing on the market right now because our motors are, to meet the FER rating, they need to be variable speed, they need to work off static pressure. So if you don't have a manometer that's reading static pressure or the static pressure tips, get out there and get one. If you haven't done static pressure, go on YouTube. They have a lot of videos with, they're about 5 minutes, 7 minutes long. Fantastic. They're going to teach you how to do your static pressure between your return and your supply. They also tell you there's a lot of coils out there that have a lot of big static resistance on it. So it'll show you how you can test your filter static or your coil static to see how much resistance we're getting through that at that time. Big thing to be doing out there. Make sure you're doing your static pressure and your temperature rise. That's it for motors. So that's our 3 motors that are out there that we're dealing with on a daily basis. Doesn't matter if we're in it's heating or cooling, that motor is running and working off static and temperature rise, whether it's in cooling or heating. We need to know that is working properly before we can go to the next step and see what else is not working properly. If we don't have the right airflow, whether it's in heating or cooling, we're going to have a problem where it's with a heat exchanger, high limit, or an AC freezing up in that mode. So ion control, we'll touch base on this a little bit. So this is, like I said, for our 97 fully modulating furnace. This is the only way to make that furnace fully modulating is with this ion control. It's the communicating thermostat. You also have the option to put this ion control on the 2-stage CTN furnace. We just have a standard 2-stage furnace and we want a communicating unit. Simple wiring, 4 wires to the stat, going to the furnace, 4 wires going to the outdoor unit. Boom, you're done. 4 wires in, 4 wires out. Not like the old communicating thermostat, which was the observer through KeepRight. The observer used to be able to hook up to a non-communicating furnace via a board called the daughter board. The ion control cannot be done like that. The ion needs to be with a communicating piece of equipment inside, whether it's an air handler or a furnace. So indoor equipment needs to be communicating to hook that ion stat up with it. Outdoor AC doesn't make a difference. We'll go through that in the next couple slides. So nice, we have a communicating outdoor unit, communicating indoor unit. Got our 4 wires hooked up. We're going to turn this baby on. It's going to look for the new indoor equipment. It's going to look for the outdoor equipment. It's going to ask you a couple other questions, filter, humidifier, UV lights, if you have that stuff hooked onto it. If you have a communicating indoor and you have a non-communicating outdoor, at this stage of the process, once it finds your indoor unit, it's going to search for your outdoor. If it does not find a communicating outdoor unit, it's going to ask you a question. Do you have an AC hooked up to it? Do you have a heat pump hooked up to it? So this is where we go through the next steps if we don't have an outdoor communicating unit, which we'll touch base with in some more slides as well. So once it finds your equipment, it's going to tell you, this is what I have hooked up. I have a G9MAE060. Here's your model number. It's going to tell you that I have a heat pump hooked up to it as well. So it's going to give you a summary and you're going to say, yes, okay. Or you're going to say, hey, search again. You've missed something. If it's missed something, do a search again. If it misses it again, then we have to go back and we have to look at some wiring. Something's not plugged in correctly. Very uncommon for the unit not to find the outdoor unit if the plug is in there. Very uncommon. So after it finds everything and you okay it, this thermostat is going to do an air test for you. So instead of guessing, it's going to run through, it's going to ramp up the blower, ramp down the blower. It's going to do a whole bunch of little things. You're going to hear it do ramping up and down. So it's doing the process for you. It's going to measure your static pressure. It's going to tell you your CFMs, what your blower RPMs were just to get to what you're getting. So once this comes up, it'll tell you, you could look at it, hey, there's our static pressure 0.66. This is fantastic. We have a great system. The furnace is going to be able to operate at this. If you see that static pressure out of the range, if we're into the 1.2s or we're real low, then, hey, we need to look at something. So great stat for that. It gives us the opportunity to measure this without using your external tools. The furnace is doing it with the motor. So once it passed that test, then we can go into the rest of the thermostat. We can configure it. It's a communicating unit, so it pretty much communicates to what it needs to do. It knows what size of heat pump or AC it has. I know what size of furnace. I just did my static pressure check. I know what kind of airflow I can pump through this baby to keep it in the parameters. Now, the background of the thermostat is just something that where you can go in and you can tweak a couple things. So equipment summary, you can go in there and see what's going on. We can go into installation, setup, check everything out. Service information, refrigerant charging system. This will help you charge the refrigerant in an outdoor unit. It's going to tell you some subcooling and stuff like that. I like to do it old school, weigh your refrigerant in. That way there, we know everything is 100%. If we weigh our refrigerant in, that's one step out of the way. We know that is right. If we're not getting our subcooling or all that is off, then we're looking at something else. We're looking at airflow. We're looking at filters, block coils. So old school is good as well to double check everything else. Software upgrades, if it's via Wi-Fi, that will upgrade by itself. If it's not via Wi-Fi, then we have to manually do a UB chipped and update it manually. Dealer logo, you can put your dealer logo on these screens as well. So an idea of if you have a furnace or an A coil or a fan coil, these screens will be lit up. When they're lit up, that means you have access to these screens. If it is not lit up and it's just like a dull gray, that's telling you that option is not available. You don't have anything hydronic airflow hooked up to that unit. If it's lit up for zoning, hey, we have zones. We can go in there and we can have a keep right zone system, which is fantastic. It's modulating indoor with a modulating furnace. We can put it on a modulating heat pump. We don't have to do any blow off dampers or anything like that. The units will modulate together with the modulating dampers to heat and cool the property. There's no setup to be done. The furnace does the static pressure test, just like we did at the starting. It runs through its air test and boom, you're ready to go. Fantastic system. If you do a lot of zoning, read up on it. It's great. Different configurations that you're going to look at: auto mode setup, heat cool dead bands, offsets. If you want to offset, like standard thermostat, we can offset the temperature to fool people, or they have a temperature thermostat beside this one. That one's 30 years old, but it's more accurate than your new one. You can fool the thermostat to look at their other thermostat as well. Reset the factory defaults. This is a great one. If you think the person's was in the background of the thermostat and started tweaking things because there's just been some weird stuff going on. You can reset this thermostat back to factory defaults, wipe it clean like the day it was in the box, restart it, and it's going to start everything over from fresh again, which is great. You don't have to start going into every setting to see what they did. Just wipe it clean, start from fresh again. Like any standard stat, scheduling on and off, smart recovery, stuff like that. This is where we can get into tweaking a little bit. Gas, heat, airflow, we can go in and tweak it up and down a little bit. But it's already checked the static pressure, so you're just tweaking it. Heat pump, AC airflow as well. Gas heat staging, you can tweak it a little bit, speed up the first stage and slow down the second stage, stuff like that. If you have a modulating furnace, you'd have modulating limits you can play with when it's going to go from 40 to 100, or you want to start it off at 60 and go to 100, stuff like that. A lot of little things you can play with. G terminal setup is a big one. If you're putting an HRV onto the board, we have to energize the G. The G is not energized on the furnace till we go into the stat and energize the G. Because we're doing a fully communication, we're not using that terminal strip for that G terminal. So we need to go in and turn it on. It's all in a manual, great little manual to read. It's a stat that you need to play with, you need to sell. So you can play with it more. More you play with it, more you're gonna know about it. If you don't sell a lot and you have a couple out there, go to gokeepright.com, download the manual, read up on it every once in a while. It's just to keep yourself informed. It's, if you're not doing it a lot, then you tend to lose what you did to the last one. So it's great just for to read up to keep yourself going. So airflows, electric heat, dehumidification, G terminal input, that can be all done on the fan coil setup. Heat source lockout, we can lock out our heat pump at a certain temperature. We can even lock out our indoor section, so it won't come on, so our heat pump will run a little bit longer. This thermostat will learn if the heat pump is running for 20 minutes and it's only -10 outside, the electric heat is going to turn on to help that heat pump get up to temperature. Some people like the heat pump to run a little bit longer. So what you can do is you can lock out the indoor unit to -10 as well. Lock out your heat pump at -15, lock your indoor unit out -10, -6, and that backup heat will not come on if it's at -5. So a little bit of tweaking you can play with to keep the customer happy. So typical wiring, this is just a standard wiring diagram for heat pumps. I always like to throw in there. It pretty much works on everything. It's simple, easy to read. 6 wires to the outdoor unit if you're 2-stage, 5 wires if you're a single stage. I always like an outdoor wired thermostat. I don't like using Wi-Fi, anything like that. Outdoor sensor, wired, you run it outside by your heat pump that's outside. Wi-Fi is taking the temperature of whatever the world's telling us at that point. But your heat pump could be sitting on the south side of the house in the sun at that time of day when it's -25 outside, but your heat pump is actually sitting in the sun and it's only -10. Hey, we could be running that baby and saving these people money. Wi-Fi is not going to allow it to run because it's telling you it's -25 outside. This is telling you what the temperature is of that heat pump at that time of the day where it is sitting, so you can get some more run time. If your Wi-Fi is out, you're not reading outdoor temperature. If you're getting glitches, you're not getting outdoor temperature. So just things to look at when you're working on this. We can do a Honeywell Stat Wi-Fi and still put an outdoor sensor on it, wired. Go that route, your customer will probably be happier. So So here's the wiring diagram for our communicating units. So we have a communicating stat via a communicating indoor unit, whether it's a furnace or an air handler, 4 wires. Outdoor communicating unit, 4 wires as well. Always run 4 wires to the stat to the outdoor unit. Some outdoor units don't need a 4-wire to communicate. Run it for the price difference between a 3-wire and a 4-wire. Run the 4-wire. You might not need the 1 wire. So 4 wires indoor, 4 wires outdoor. So here is where we get to, we have a fully communicating indoor unit because we know we have to if we want a communicating stat. People want to keep their AC outside for now. We'll place it in a couple years. No problem. We'll just hook it onto our terminal strip downstairs at the furnace. And when we first turned our thermostat on, like I said, it's going to search for an outdoor unit. If it doesn't find one, it's going to ask you if you got one. Answer the questions and move on. If you go and you add a AC to a communicating system after the system's communicating, when you first hooked it up, there was no unit outside. You need to go back to the stat and you need the stat to tell it to relearn. So the stat is going to relearn itself. It's going to look for its indoor unit and it's going to look for an outdoor unit again. We start the process over if we've added something on or changed something. If we have a communicating wall stat and a communicating indoor unit and the customer has an existing heat pump or a 2-stage air conditioner, if they do, we need to add another board because it's 2-stage and it's heat pump. We need to add a communicating relay to that furnace downstairs so everything will talk properly, and we need to add an outdoor sensor. We're adding an outdoor sensor because old units we cannot use if that one had an outdoor sensor, or most units, the older ones, don't have outdoor sensors. So we need to add one so the stat can read the temperature outside. So be mindful of that as well. And that is all I have for you guys today, and girls.
Thanks, Craig, for putting that together for everybody. Does anyone have questions for Craig before we move on? All right, so thank you guys all for joining today. Next is Wolves Express. So I don't know if you guys have registered for that, but that's tomorrow. And then on Thursday we have Duckless. So looking forward to seeing more of you guys. And again, thank you for your time today. Hopefully it was helpful for you all. Have a good day.
Thanks, everybody.